I mentioned the creep mechanism. Okay. Okay, I just want to drag these things down. Okay. So in the slides, we have shown you those three mechanisms contribute to the creep deformation at very high temperature in the bottom part, which we call is bulk diffusion, because at that time the very small amount of stress, but temperature is high enough to melt the material. So basically, you can imagine the atom at that high temperature can move so fast, like liquid, so they can travel easily. So this is called bulk diffusion. If you reduce your temperature and there is a kind of more grain rather than just a limited grain, so there's more grain, then there is a huge gap actually. So then there's more atoms can travel through the gaps, which is called grain boundary diffusion. But if you, on the other side, if you increase the temperature at a similar level, and now you are stretching the material like a tensile test, and in a kind of a micro scale, so the grains kind of what I mean is more in a grain level. So just look at a single grain, which have a lot of atoms. It will have some dislocation. So I will explain that to you soon. And they are governed by the equation which you have told before, this equation. So recently it is called power law creep because you have a sigma stress, which is now kind of dominated term with a power n here. Normally n is larger than 3. So it's kind of have a major effect on the creep strain rate. Okay, so that's why it's called power law. But microscopically, it's dislocation. So what is dislocation? That's the main questions we want to answer in this lecture. So if you read the definition here, dislocation is a linear crystallographic defect, okay, which contains an abrupt change in the arrangement of atoms. So you will see two words, atoms. There's a defect in the atoms. So what that means, if you have a perfect lattice, so that for a cubic in a 2D view, so you will see they are kind of have a perfect bond with an equal kind of distance and forms some covalent bonds, and they are looks like very regular. Okay. How about if you have a lattice with dislocation? So what happens is, like, if I remove these 3 atoms here, just due to some manufacturing, there's some defect, which I have this kind of a small grain without these atoms. So now you can see how there actually has a defect here. So missing atoms. Because this bond looks very weird as a so long covalent bonds. Normally they will attract itself, so it will form a bond more like this. So these atoms, imagine that is moving to that side, okay, and something like that. Okay, atom 1 here. So eventually it will look more like that, or even narrow down. So let me show you a lattice with dislocation, which is just repeat that figure in this graph. Okay, you can see actually they're not regular anymore. So that is the dislocation. It's a defect in the arrangement of the atoms. Okay, think about daily life example, if you search dislocation, you will find actually you end up seeing a lot of image of the bone, a bone dislocation. So I guess most of you, when you were very young as a child, you actually got something dislocation of your bone because some of your parents or your friend pull you very heavily, so you have your dislocation of your bone. So similarly, here is a similar idea. You kind of have the dislocation of atoms, which is not in the right place it should have, or you have missing part of the element or atoms here. Okay, so what happens if you load your material, for example, a plate, macroscopically you load it, and then in a micro scale level, which you will look at this atom arrangement. So it's basically we are looking at a stress. You actually generate some shear stress, basically like pushing these atoms here. And what's happened here, like I draw here. So we see the first column. This is the basic of the atoms here. You can treat this part is the including the things I cut it off. Okay, this kind of atoms is in a dislocation state, and if you apply a stress, what happens is basically if you look at this atom here, will kind of tend to fail. So this bond will be cut off, and this bond eventually will want to attach with another atom. So you will see actually this covalent bond will move from the right side to the left hand side, which looks like this. Okay, so the dislocation now kind of move from number 1 column to number 2. You see the green region now move to number 2. So now dislocation is sitting at this part. If you think about these lines, you can treat it as actual atoms here, and it's moved to the number 2 column. And if you further apply stress, and you will see this one, the bond will cut and move to this one as well, and similarly for this one. Okay, so eventually what's happened is it will looks like that. So this is the final result after you apply a shear stress to your defected atoms arrangement. So that grain will become like that. And the movement of dislocation basically from number 1 eventually move to number 4, right? So this dislocation begins around here, number 1. Eventually you move to number 4 in a case like that. And if we give you the definition of slip, so the slip is basically the name for the dislocation movement. The whole movement is called dislocation. If you just think about dislocation itself, it's just the defect in the atom arrangement. Okay, the slip is more like a gliding or shear. It's a dislocation movement, which allows atoms to glide over each other at a low stress level, but of course at a high stress level it will slide even fast. Okay, so let me showing you some animation, which you see. The first video is the slip by dislocation glide, basically the same picture you have seen before, but it's not an animation. So you apply shear stress on this kind of defected atom. Now it looks like that. Doesn't matter, it's kind of have some missing atoms here. Apply shear stress, what's happening, you will see. You can see it's moving from the right side to the left hand side. Now finally become the picture like that. And during the video, you will see there is a intermediate state. You see this dislocation you have seen before. They are equally the same, basically. And if you can see a sign here, which is called Berger vector, if you search that in Wikipedia or online source. And basically, it's a sign here, like that. It means the horizontal line means the slip direction, which is the horizontal direction, okay? And if you look at the vertical line, that's the slip plane, which is the slip plane here. That's called that is called plane, okay? It's basically the dislocation part where it is moved from left and to right. Okay, that's the notation for the slip. And there's another video which is showing you slip by movement of the whole lattice plane. So sometimes you apply a very large stress, and you will end up have the whole bottom will move at the same time, not just one by one. If you look at that, oh, sorry, you can see it's more like a shear, a big sliding. So all the atoms at one time will move from the right to the left. Okay, so that's the animation of dislocation for this typical type. And if you look at an even better dislocation, which give you the idea, dislocation happens within the grain. And you can see the video. And there's several grain. And we will zoom in to one grain in the middle and see what's happened for the dislocation. Okay, now you zoomed in, you can see basically not they are doing the whole movement or just doing this single glide one by one. Dislocation can also climb like the final part, which is very interesting. We can watch that again. Okay, at first of all, there's some shear force which applied, and you can see the glide. And now here is the climb. So the dislocation is climb, which is normally used to kind of overcome some obstacles, so which you can see later on. Okay, so there's some concept here. This dislocation force, the line of edge dislocation also provides an easy diffusion path and act like a pipe. Basically, is the area here, the shade area here. Okay, that's kind of defect part, which is much easier for the diffusion path, like the atom to move around. But we are talking about dislocation, basically just the dislocation itself. Okay, and let me explain this power law dislocation a bit more. So, like you watch the video, there's a mechanism called dislocation climb. I need to drink water. I don't know why I couldn't pronounce that well. Okay, dislocation climb. And basically, it's like if you have a obstacle, normally in metal you have some precipitate, something like a particle, and your atom trying to like do these dislocations, but it cannot because you block it by this particle. Then essentially they will find another way to overcome it, basically going up, like the video show is climb. So that it going to the vertical way so that it can overcome these obstacles and or particles. Okay, it's like out of glide plane stress, basically because you apply a stress in that direction, which helps this dislocation climb. That's often happens in this uniaxial tension test, I think, because you're helping the atom to climb over obstacles. So one of the atom will go up and jump over these obstacles and finish the dislocations. Okay, that's very interesting, actually. So this is another picture to showing what's going on for these atoms. They're basically going up, and this is the hot plane which the atoms trying to climb over it. Okay, and I think that's it. And the equation for that is we have shown you several times, and that's the most important questions in creep. Okay, we repeat that again, where n in the range from 2 to 7, typically 5. Okay, and it is very sensitive to the stress, because that term is a kind of power law. It's really make your stress dominated the whole term. Now let's come back to the deformation mechanism map, which you can see here. We have finished the bulk diffusion. We have grain boundary diffusion and power law creep diffusion. Dislocation is not diffusion. Okay, and we normally tend to plot it even more precise rather than just explain that in this way. So we need to plot some boundary between this mechanism. They must have a boundary, right? You have different. So if you look at the blue curves, which is around here, and the boundary line here are the losses of the or envelopes of the point at which two mechanisms have the equal creep strain rate. So if you look at the first one, dislocation creep, we have this equation for creep strain rate, right? If we have the grain boundary diffusion creep, and we have this equation from the last lecture, which is relatively dominated by the grain size, and the stress now is the linear term. The stress is not that important. And if you want to find the boundary between this one, GB, grain boundary diffusion, and the dislocation, you will actually make that this equation equal to that. Okay, number 1 equal number 2. We'll actually cancel this out, right? So basically, you will end up have this term equal to that term, and so you eventually will plot something stress is related to temperature. Okay, bear in mind the Q here is not the same. There's some extra consideration for the activation for grain boundaries, so they are not the same. That's why you will plot something where is related to the temperature. And similarly, if you have another mechanism which is called bulk diffusion, which is in the bottom here, and they have the equation very similar to grain boundary, but less sensitive than the grain size D. And similarly, Q is different with the dislocation creep. And you can such that this one, you can enable this equal to the dislocation creep strain rate. And again, you will get the equation for this line. So probably here, yeah, from here. And there's a vertical line here between this and this. Again, is obtained by equal this one, grain boundary strain rates equal to the bulk diffusion creep. And you will see actually cancel out the temperature. In this case, the Q is the same for these two. So you will cancel out the T. and in the end, it's just relevant to the stress you applied. Okay, but of course, the stress kind of also cancel in this case. But again, I think this equation is not exact the right term. I mean, it's not the complete term for that answer. So the end up have the stress also have some difference. But anyway, that's the basic idea where you get this boundary line. And I'm not. Let me come back to this later. I need to answer some questions. Okay. Do we need to remember these equations? No, you don't need to remember the equation for the second and the third one. But the first one, you need to remember the equation, okay? You only need to remember the dislocation creep equation. That's my suggestion. And for this boundary line, you just remember that very roughly. If you want to draw it, just draw it roughly. I don't expect you can draw exact solution for that because for different material it's different. And so you basically remember when you draw it, there's some activation temperature about 0.2 T over Tm. And this line basically is kind of nonlinear line come to here, around here. And there's a dashed line which is divide the power law creep with the dynamic recovery. And there's another things here, about 0.4 roughly. And you can have diverged. There's a diverged curve which give you the boundary between elastic deformation and the grain boundary diffusion. And at 0.8, there's a kind of a vertical line. This should be vertical between diffusion and grain boundary diffusion. Okay? You need to mention at least these things: diffusion creep, dislocation creep, and have this separate mechanism for the diffusion creep, grain boundary, and bulk diffusion. And also remember to plot the axes. So axis from 10 to -1, 10 to -6, and theoretical strengths, and there's a shear yield strengths. Okay, so a lot of detail you need to remember, I think. But I think fortunately, I guess in any case, it would become an open book assessment. So if you are testing, you will, if you have these questions, you just basically copy from your lecture. So don't worry too much. And basically, the most important is to understand this mechanism. That's the idea behind this creep mechanism map. Okay. And there's a very complex map for a copper material measured from experiment. Just give you the idea when the scientists how to plot this map from the measurements. So again, it's relatively similar things, which you plot this shear stress tau over the shear modulus is the exactly same axis, and the temperature normalized by the melting temperature. And you will see a lot of contour line. What's that? If you look at that, it says strain rate. So this line is for different grain size, so which contribute to different strain rates when you calculate that equation, and that give you a lot of contour line. The point here I wanted to explain, not to ask you to remember anything of that, just to show you a typical map for material, engineering material. So you can see here is very different actually. At the starting point, it's not from 0.3, it's actually from 0. So that's because that is the copper. That's a very soft, kind of soft metal. If you think of steel or titanium, they should start from 0.3. They wouldn't creep at a room temperature. Okay, and then there's some nonlinear curve like that, which basically this is the one for the power law boundary, and then there's some line which give you the boundary between the diffusion and the elastic deformation. Okay, and for the engineering application, you will see here, I highlight here, only this region is of interest. Is used to forming or shaping. So basically you make your, like a copper rod into a sheet of material, like a copper film, okay, or copper wire or something. That's the temperature and the stress normally used to forming and shaping. And this is more like an application side from this map. And if you want to use that in the structure application, you don't want that creep very quick. So most of the time it's in this region. So temperature shouldn't be too high. And you will see the stress varied from the bottom to the top. Okay? That's for the application argument. So point to remember here is creep is strongly stress and temperature dependent. So there's a stress exponent N and activation energy Q, which are normally determined by the experiment. And also this deformation map governed by different mechanism, which is very interesting. And basically dislocation and diffusion. Okay, and diffusion can classified by bulk diffusion and grain boundary diffusion. Okay, and these are the kind of, they are all represented by this deformation mechanism map. Now we move to the creep rupture and design for creep resistance. That's more like a fractography of the material and the creep failure. So now we are moving to the region where in the final region, tertiary region, where you have the creep strain rate growing very quick at this regime and eventually will fail because the strain is too large and basically causing some rupture of the material, like the fracture mechanics we're talking about, but although they are not sensitive to the notch size here, they're basically a lot of void developed during this stage. And creep rupture diagram for time to failure at different temperature. So if you plot log sigma in a relationship with the time to failure, you will get some relationship like that. Basically means if you have a higher stress at this point, then that means you will fail your material much quicker. That's easy to understand. And if you increase your temperature, that will also kind of lower your life. If you look at the TF, it's the creep life. From this point, we'll go to that point. So it's kind of life will reduce in this way. Okay. So in the engineering application, we have this equation to describe this relationship, which is called Monkman-Grant relation. What that means is basically plot the relationship between this is a constant K and the creep strain rate, which the creep strain rate we have used before, in a relationship with the time to failure. This is different with the things we talked about before. We normally are given the final failure strain, which is like 0.1. If you're not given that, how can you determine TR? TR originally is determined by epsilon F over epsilon S dot. But now if you're not given that value, how can you get this TR? Which basically this is the equation to get the TR, the time to failure. Okay, and K is constant, C is constant. Okay, so they are mostly determined by the experiment, and you can rearrange the equation, which give you that log epsilon s dot will have a constant here, and minus 1 over c log TR. So let's see how it looks like. So this is the experiment who actually get these data for log epsilon s dot log TR. And they can find is actually this reflect this linear equation, but in a negative gradient. Okay, so that gradient give you minus 1 over c. And this equation is very useful as well, just to help you work out the creep strain rate. Sorry, if you're given this creep strain rate, you can work out the TR, vice versa. Okay, so like I said, the final stage of creep when void and cavities begin to appear in the material. This will reduce the cross-section area in the local stress and accelerating the creep strain rate. Since epsilon dot is kind of a function of sigma n, okay? So which will leading to plastic instability and failure. The failure is ductile and the result of the deformation process. And there's two types of cracks or voids are associated with creep rupture, which number one is wedge-shaped crack, which we can call it W type. Number two is round-shaped cavities, R types. So let's see, first of all, a video which will contribute to the first type, W-shaped crack. So this is called grain boundary sliding. So you have the grain boundary between the grains, and because the shape of the grains change, diffusion creep or dislocation creep, so the neighboring grains have to deform in a compatible manner, otherwise it's not force equilibrium. And at high temperatures, grains in metal and ceramics can move against each other, so that is called grain boundary sliding, which is here. You can look at here. So it's like sliding against each other, so that gives some deformation, okay? At this stage, it's quite large scale. So W-shaped cracks developed mostly at these triple points. What is triple point is, if you look at grain boundary, it's basically this straight line from a point or junction here, and it's roughly, you can see here, it's the same. That's have a straight line and have a triple point here. It's a junction of three grain boundaries, and it is enabled by the grain boundary sliding here like this. Okay, so now once you load it, this grain kind of sliding to the direction I'm plotting, and this other two is also sliding, so that you generate some gaps, which that is the kind of cracks, which we call wedge-shaped crack, or simplify that, called W-type cracks. Okay, similarly you can see here or here, they're all due to the grain boundary sliding, and it can be assisted by diffusion as well. The process is favored by the high stress and moderate temperature, so often follow the dislocation creep, like I said. So you can see here, this is one of these wedge-shaped, because there are three grain boundary here. and sliding here. And similarly, you can see here as well. Okay, some big ones here as well. So that's the W-shaped crabs. And now there's a round-shaped cavity formed at grain boundaries through diffusion of vacancies. In other ways, kind of diffusion of atoms. And their accumulation at the grain surface. Okay, so that means if you remember that picture, if you load it here, so what happens is you will see there is some, like I drew before, I think this is called kind of diffusion of vacancy. Okay, here you form some kind of void or cavity here. Okay, and all the atoms will move to here. And here is become thicker, but here is kind of have some vacancies. So there's some cavity formed like that. And eventually coalescence of these cavities will forge into a crack, which is assisted by the grain boundary sliding, R-type cracks. And formation of R-type cracks kind of here. So imagine that is the load direction, and you form some cracks here. Okay, you can see some. So the atoms move to away here, and some of the vacancy move to here. Okay. So the process, like I said, is favored by the high temperature and the low stress. So in high temperature, it's more likely to happen. Okay, it is often followed by diffusion creep. Now, this is the typical fracture surface, where you can see the intergranular fracture with cavity in the fracture surface. And intergranular fracture is like intergrain. So you have the grain here. The fracture will go through here. But you can see this is the kind of the clear kind of wedge shapes with a triple point, and you will see this surface kind of must be from the cavity. And this kind of dot, small point here, is more from the R-type round shape crack, because the cavity, you think some cavity formed here. Also, there's some some cavity formed between the grain boundaries, probably here. Okay. So summary of the creep, like we have spent about 2 lectures on this topic. It's very interesting. There's a lot of mechanism, especially the microscale, to help understand what's going on here. So basically, this is the highlights. You need to remember the creep is the process of 3 elements: stress, temperature, and time, and it is mostly described by this